Hello everyone, I'm Zeng Cheng. We'll study the last part of this course together. In our course, lots of mathematics will be involved. However, math is just the same as words. It's a tool to express ideas. Therefore, in our course, I'll try as much as possible to show the ideas expressed by the mathematics to you. Hi, in this lesson, we'll discuss the relation between LTI system model and the causality and stability of the system. In this section, we mainly discuss how the system model of a LTI system will affect the causality and stability of the system. Let's study the causality first. If a LTI system is causal, its zero-state response should not appear before the input is added to the system. In other words, if the excitation is zero, then its corresponding zero-state response must be zero too. So we can deduce that the necessary and sufficient condition for a continuous LTI system to be causal is that its impulse response h of t equals to 0 must be held when t is less than 0. Hence, h of t must be a causal signal. For a discrete LTI system, the necessary and sufficient condition of causality is that its unit response h of k equals to 0 is held when k is less than 0. Hence, h of k is a causal sequence. Next, let's talk about the stability of LTI systems. In general, we refer to stability in the sense of bounded input and bounded output. That is to say, if the zero-state response of a LTI system is bounded for any bounded input, then such a system is said to be stable in the sense of BIBO, which means bounded input and bounded output. Based on this definition, it can be proved that the necessary and sufficient condition for a continuous LTI system to be stable is that the absolute integral of the impulse response h of t from negative infinity to positive infinity should be bounded, which is called absolute integrable. For discrete LTI systems, the absolute sum of its unit response h of k from negative infinity to positive infinity should be bounded, which is called absolute summable. However, absolute integrable h of t or absolute summable h of k is unnecessary to be causal. If the system is causal, which means h of t and h of k are causal signals, then our discussion about its stability can move forward a little more. For a continuous LTI system, if it's causal, then the lower bound of its absolute integrable condition becomes 0. Therefore, we can deduce from it that if all the poles of the continuous LTI system are located in the left and open half of plane S, which means the amplitude of its impulse response will decrease exponentially as t approaches to positive infinity, then such a system must be absolute integrable. Hence, the system is stable. For a causal discrete LTI system, its stability can be analyzed similarly. If the discrete LTI system is causal, then its unit response is a causal sequence, which means the lower sum limit will be k equals to 0. Thus, the necessary and sufficient condition for a causal discrete LTI system to be stable is that all the poles of h of z lie within the unit circle of the plane z. Because under such a condition, the amplitude of its unit response will decline exponentially. For k from 0 to positive infinity, the unit response is absolute summable. Based on the above discussions, we can conclude that the necessary and sufficient condition for a causal continuous or discrete LTI system to be stable is for a continuous system, all the poles of its system function must lie in the left and open half of the plane S, while for a discrete system, all the poles of its system function must lie within the unit circle of the plane Z. Next, let's take an example to analyze whether a system is stable or not. In a causal discrete LTI system as shown in the system diagram, k is an undetermined coefficient. We want to know the range of k which will make the system stable. Firstly, we can get the system function from the diagram, where k is a coefficient in the polynomial of its denominator. Thus, k will affect the poles of its system function. Based on such a denominator polynomial, the relation between k and the poles can be solved. According to the necessary and sufficient condition for a causal discrete LTI system we discussed above, all the poles of the system function should lie within the unit circle, which means the module of all poles must be less than 1. After discussions about the cases where the poles are real or conjugate complex number, we can note that such a system is causal and stable when k is greater than 0 and less than 1. Finally, let's make a summary of this lesson. Firstly, the causality and stability of a LTI system essentially depend on its system model. Secondly, the impulse or unit response of a causal system must be a causal signal, which is also the necessary and sufficient condition for an LTI system to be causal. Thirdly, the necessary and sufficient condition for a LTI system to be stable is that the impulse response is absolute integrable or the unit response is absolute summable. Fourthly, if a LTI system is causal, then the necessary and sufficient condition for its stability can be expressed equivalently as: for a continuous system, all poles of its system function must lie in the left and open half of plane S, while for a discrete system, all the poles of its system function should lie within the unit circle of the plane Z. And that is the end of this lesson. Bye.